We have been looking at quantum computing implementation aspects with regard to the quantum mechanics per se. So, carrying on in that direction, I start off with the idea of quantum computation in the process of how the steps are to be labeled. So, the 0th state or the first step is essentially the preparation phase, where the initial preparation of the state defines a wave function at time t starting point t naught equal to 0. So, that is the first step, and the first unitary operation should take it to the state which could be our state of interest, which is applied to, let us say, the unitary operations or logic gates which go ahead after that. So, this particular eventual operation procedures are sort of like state evolution operations, which are evolved by a specific sequence of unitary operations. And finally, is the measurement process, where the quantum measurement is going to give rise to the projective component, and the final step is the measurement, where the projection will be made, as quantum measurements is projective in their character, and essentially it is a collapse by measurement of the state. So, that is the basic principle which we have been following. In terms of the logic gates, we have been discussing the various kinds of logic gates. The definition can be simply put as any possible operation on a qubit register that can be represented in terms of suitable sequence of actions of elementary logic gates are the ones which are in use. Introducing a complete set of logic gates are hard, because unlike classical computers, the number of logic gates needed as the number of qubits increase can be very large. It is true that for a single qubit operation, there are finite number of logic gates which can be defined, which could do the entire computations that are necessary, but when it goes to higher number of qubits, this is not quite possible to do it. Here is an example of a unitary operation which sort of undergoes, let us say, the phase shift versus the rotation versus once again another kind of a phase shift. In general, it can be proved that any 2 by 2 unitary matrix can be decomposed into various kinds of rotations or amplitude changes or phase changes, and thus the unitary operations are always possible to be labeled in terms of these kinds of several single qubit operations that can be looked at. So, this is true, as I mentioned earlier, for a single qubit concept. So, that is the basic point which has been stated here. For any arbitrary 2 by 2 unitary matrix may be decomposed into 1, 2, 3, 4 components, because this is how these can be represented as. We have been discussing a lot about the superconducting qubit devices. So, let us look into this a little bit more in conjunction to these gates and qubits that we are talking. In general, any quantum mechanically coherent system could be used to implement the ideas of quantum computing, as we have talked about, and we discussed single photons earlier, nuclear spins, NMR, trapped ions and atoms that we just discussed in last lecture, and superconductors is the other kind which we will be looking at now. Advantages of solid state implementations obviously rely on the fact that it is a possibility of the scalable implementation is quite high in these cases, and superconducting devices provide the minimum levels of decoherence among solid state, partly because the energy loss for these cases are very minimal, and so this is one of the biggest advantages. So, it is a very promising implementation of the qubit. There are two kinds of qubit devices, either based on the charge or the flux degrees of freedom in these particular cases. And so, based on these, the superconducting qubit devices can be looked at. The Cooper pair box qubit is based on the idea that it has the Cooper pair located in two parts. One is the bulk superconductor, and there is the part which is the main part, which is connected to the box and has the DC bias gate VB or the pulse gate VG. A scanning electron tip measures the ACT tunnel junction values, and this is in volts, and this is the value which is being measured in terms of the tunnel junction signal that is being seen. This is how the schematic representation of a Cooper pair box looks like. Mathematically, we have this Hamiltonian, the Cooper pair box qubit has a system Hamiltonian, which is one part is the tunneling top, the other part is the energy state of the nth Cooper pair. The two components can be controlled by using the DC voltage or the pulsed voltage. When a sudden square pulse is applied to the gate by using the pulse gate VG, then the coupling occurs between the states. So, we have a coupling between the 0 and 1 state as well as the 2 and 0 state. The square gate pulse lasts for some time, delta t, which ensures that there is a temporal evolution of the system, and that is given in terms of this Heisenberg integrated form. And then the square gate pulse lasts for some time delta t, which means that the system propagates in terms of the Schrodinger equation, and as a result there is this exponential term which appears. When the Vg returns to 0, then the resultant is a projection of the state with respect to the current evolved system. The probability that the state does not return to the ground state, therefore, can be seen as 1 minus the probability of the return, and that gives rise to a value which is shown here, and it depends on the energy gap and the amount of time which has been applied. The Cooper pair box qubit, therefore, would evolve in terms of the applied gate voltage as shown here. The scanning electron trip voltage will be registered in terms of the values which are seen. The initial state is prepared in state 0. The gate pulse leads to a superposition of 1 and 2. After the pulse, the state is in superposition of 0 and 3. Incoherent transitions from 3 to 0 lead to the detected current in the scanning electron trip. The Cooper pair box qubit, therefore, has a pattern which essentially shows that as the current changes in terms of the applied voltage, it is proportional to the excitation after the pulse. The result is remarkably similar to the actual data which have been seen by these experimentalists, and the horizontal axis is proportional to the pulse gate voltage, represented by in units as effective number of Cooper pairs Q. The observed coherent oscillations persist for longer than 36 cycles, essentially showing the quantum nature of this qubit, and these have been measured by several other groups as are discussed here. This is the article which was the one where this data has been taken from. The observed coherent oscillations persist for longer than 36 cycles, essentially showing that this can form an excellent coherent system which can last as long as the oscillations exist. That means that the coherence is being maintained. The other important aspect is the superconducting flux qubit. So, in this case, so the earlier one was the Cooper pair case, and this one is the two quantum states which are being looked at in terms of the flux qubit. The coherent time evolution between the quantum states were observed. The flux qubit consists of 3 Josephson junctions arranged in a superconducting loop. Two states carrying opposite persistent currents were used to represent 0 and 1. The external flux near half the work function of h over 2 e is applied. This is either going counterclockwise versus clockwise. A squid is attached directly in this particular study. So, in a megawatt line provides microwave current bursts inducing oscillating magnetic fields. The current line provides the measuring pulse and the voltage line allows the readout of the switching pulse. So, this is a technique which was discussed in this article which is shown here, and as it can be shown that it is a very small device, 2 microns is a size dimension as representative. So, roughly this whole process occurs in a zone which is a few microns only. The flux qubits are being measured in terms of the two energy levels of the qubit. The qubit energy separation is adjusted by changing the external flux. The resonant absorption peaks and dips are observed. The dots are measured as far as the peak dip positions obtained by varying the frequency of the microwave pulse. The continuous line is a numerical fit giving an energy gap of about 3.4 gigahertz in agreement to numerical simulations. Once again, this is something which has been discussed in detail in the article. We are just showing certain results just to understand that there are different ways of using the superconducting conditions for creating the qubits. When the microwave flux is about 6.6 gigahertz, then there is a linear dependence of the Rabi frequency of the microwave amplitude, which is a key signature of the Rabi process, and the decay times are up to 150 nanoseconds, result in hundreds of coherent oscillations. So, these oscillations which are being seen here, the switching probability are the hallmarks of the Rabi oscillations. Rabi oscillations essentially mean that the population can cycle between the ground and the excited state, in a sense that the coherence of the system is being maintained between the two states as long as the field is being provided to make the oscillations work. So, the ground and the excited state therefore have been set in such a way so that there is a coherent cycling going on, and that is as long as the cycling is perfect. So, it follows the sine squared rule in terms of the oscillations. Different microwave pulse sequences are used to induce coherent quantum dynamics of the qubit in time domain. The Rabi oscillations occur when the microwave frequency equals the energy difference of the qubit. The qubit oscillates between the ground and excited state as mentioned. The resonant microwave pulse of variable length with frequency that is equivalent to the gap is applied. The pulse length defines the relative occupancy of the ground state and the excited state, and the switching probability is obtained by repeating the whole sequence of re-equilibrium microwave control pulses and read out typically 5,000 times. So, this was the essential proof of the use of superconducting flux qubits. Now, let us look into a little bit of the different areas of quantum computing that we have talked about in many different ways. Quantum algorithms, we have looked at quantum complexity, quantum cryptography, quantum error correction, quantum information theory, as well as there are many others like quantum control, game theory, and so on and so forth. Let us take a stock of the developments as we do a bird's eye view of all these different applications. So, in terms of the different areas, let us see how the field also has developed from the in terms of chronology. The area of quantum algorithms have shown a major development from 1994 in conjunction with the quantum Fourier transform concepts. which gives rise to exponential speed up. And Shor was able to show factoring and discrete log applications. It says that given a n bit number, it can be factored into products of two numbers. The reverse problem of multiplication is very easy. The classical best known system is of the order which can be presented in terms of exponential, whereas the quantum is of the order of n squared. So definitely there is a exponential benefit in going to the Shor's case, and this was first reported in the 1997 paper by Peter Shor. So the basic discovery came in terms of the quantum Fourier transform implementation as well as error analysis, which he was able to show successfully in 1994, and the implication of the fast algorithms for factoring has impact on the Church-Turing thesis in terms of theoretical aspects, as well as it also has the most important practical implementation in terms of the breaking of crypto system codes, because the RSA, the popular cryptography analysis of the system, is based on the idea of having a large prime number that cannot be factorized that easily. And so that is the point where the practicality of this became a very important point. Next came the in that region came some more developments which were shown in recent times, where it is a Hallgren-Pels equation. It is a mathematical problem which finds that given a term d, find the solutions of x y to the above x squared minus dy squared equal to 1 solution. The classical best known in this case is 2 to the power root log n, assuming the generalized Riemann hypothesis, whereas in the without any assumptions it is d to the power 1/4. In quantum it is a polynomial in terms of log d. So this is also a very important development in recent years which has come through. There has also been some more developments by in terms of the hidden subgroup problem. Given a function f on a group G which has a hidden subgroup H, the state function f is constant on each coset AH, distinct on different cosets. The task is to find the hidden H function. The factoring of this Pels equation both reduces is efficient quantum algorithms are known for these kinds of cases, which is the Abela groups. The question is whether the hidden subgroup problem for non-Abelian groups exists or not. So there are two biggest cases. One is through the graph isomerism to reduce it, which is possible for the symmetric group cases of Sn, whereas the other of the dihedral cases, shortest lattice vector, reduces into it. So the classically best known for this particular case is 2 to the power log G case, whereas in quantum case, as shown in recent work, it is of the order root log mod G. The other important development in terms of quantum algorithm has been the quantum search, which shows polynomial speed up, and it is mostly important, and that is the Grover search. It states that given n bits, find an I with xi equal to 1, which is the solution, and given the bits we have to decide whether it stays within xi equal to 1. The classical term for this is in terms of order n, whereas in quantum case it is root n, and so there is a polynomial speed up in this particular case, and this was first shown in 1997 by Love Grover, and since then it has become a very useful one. In recent years there have been many combinatorial and graph problems which have also been utilizing this principle. There is this other area of quantum walk which helps in terms of poly and exponential speed up, and it is been rapidly developed as a result of some of the recent work by Vazirani and others. It is a classical random walk on graphs starting from some vortex repeatedly go to a random neighbor, and many algorithm applications exist on this. As the quantum walk on graphs, even the definition is non-trivial. For instance, classical random walk converges to a stationary distribution, but quantum walk does not, since because its unitary is reversible, and therefore it is supposed to have a huge development possible, and elementary discreteness which involving n integers decide whether they are all distinct or the same. So, this is related to the quantum walk problem. So, in case of classical it takes order n, whereas in case of quantum it takes n to the power 2/3, and it is important for applying quantum walk on Josephson graphs, and some applications in this area has been looked at. These are mostly very theoretical based problems which have been developed, and some of these are being just shown here for completeness. Another area in recent times have been the development of a formula evaluation point in the quantum walk area, which utilizes the idea of the Grover search or function, and in this case this is a generalized formula where again the classical would be of the order n as in terms of the search problem, whereas the quantum would go in order of root n, and we can apply the quantum walk principle on the formula graph by with weight carefully designed for inductions to the work. So, these are the various different kinds of algorithm developments which have been seen in recent years. This has been provided just to ensure that there is a completeness in the developments that we are discussing, because in most of the implementations that we have looked at, we have not really focused on the idea of the algorithm development much, because that is more of the theoretical development angle, and in terms of algorithm we have been using most of the ideas of the algorithm developments in terms of implementability and showing that the implementation realistically is doing the job of the quantum problems that we are looking at. The other very important aspect of the development that we have been looking at is the understanding of the fact that we are indeed using the appropriate gates, and they have to be universal in the sense of applicability to the quantum world. And as we know, the C naught which is a 2-qubit gate, and the set of all possible 1-bit gates forms a complete set, which we have discussed earlier for lower set number of qubits. As the set size increases, multiple combined qubit set gates can be redefined, but the main basis of the 1-qubit gate as well as the C naught are the important ones to initially represent. C naught often may have difficulty to realize physically because of the implementability aspects of quantum computing, and so it has often formed a benchmark for the idea of understanding whether the implementation of the so called quantum system for quantum computing is really working in the right direction. Let us in this particular case look back into one of the other implementations which we have also discussed earlier, which is the diamond crystal structure, in which we use the donor spin electron as a qubit in this case, and the idea is that the silicon atom which forms the basic diamond structure is a group 4 element, and so any dopant in terms of phosphorus in this would essentially mean that it is a extra electron that is coming because of the group 5 element, and that is the idea of having the donor electron spin as a qubit in this particular arrangement. So, a phosphorus 31 electron spin is the one which is being utilized as a quantum system for this computing application. Here are certain aspects of the facts that isotopes of natural silicon are the ones which are shown here: 28 silicon, 29 silicon and 30 silicon. The most common abundant one is the silicon 28, which has 92% availability in this particular case, and so it has it's a spin half system in terms of the nuclear part, whereas the donor electron, if we are considering from the phosphorus atom, it will be the spin of the system which we will be looking at. And so the natural phosphorus, which is P31, also has a spin half system. Then natural phosphorus, the good thing about it is that it is 100% P31. So in the effective mass approximation, electron wave function is S-like, because it is the single electron which is going to be around all the spin half systems of the nuclei, and so it will have a spherical symmetry for the electron wave function that can be utilized. So in terms of application for quantum computing, this would be almost like a solid state atom in some sense, where there is a single electron which is being looked at, and that was the part of the work which was shown, where there were two different works which basically focused on this particular area. One was the Kahn's work in Nature in 1998, and followed by the work in Fizerbe in 2000, where in both cases the donor is the phosphorus 31, and the qubit therefore is the nuclear spin, and the qubit-qubit interaction is due to the electron spin. So this is an interesting concept where the qubit itself is the nuclear spin, which is a spin half system of the silicon in one case and silicon germanium in the other case, and both cases the interaction part is provided by the donor electron, where the electron spin acts in terms of interacting the two qubits. One of the most important aspects of quantum computing qubit is the fact that not only the qubit has to be very precise and proper and be controllable and all right. However, it also needs to have a situation where the qubit may be able to couple very effectively with the other qubits, and many cases the difficulty often has been that although a qubit has been very effective in itself as a good qubit, quote unquote, in its different aspects of interactions, gates, decoherence even. However, it may suffer from the fact that once the time comes for it to be able to communicate or translates its information or do something collectively, the inter-qubit interaction is something which are often very, very difficult to take care of. So there are situations where inter-qubit interactions are going to be extremely important in defining as to how good of the quantum computing can be implemented as a implementable device. And so in these cases, the individual qubits are represented by the nuclear spin, which are very conveniently being connected across the qubit-qubit interactions through the electron spin which is coming from the donor. So that is the beauty in both these particular aspects that have been shown, and this is one example of how it has been shown here, where the J gate of the particular electron spin is being applied from the external field, whereas the internal qubits are being connected by these two cases. So the spin 1 and the spin 2, this exchange interaction between the two are the interesting use of coupling between the two qubits, which have been enabled by a result of this kind of a interaction. However, even here the sources of decoherence exist, and that could be due to interaction with photons. It could also be due to the application gate errors which are being provided, and there has been a lot of work on this area in terms of the different interactions that can happen for the silicon nuclear spins, and a lot of work has then on been carried on, as these seem to have very interesting developments in terms of quantum computing. One of the most important aspects, as we have been discussing all the time in terms of implementation, is that we would like to have quantum systems, qubits, which are most relatable to the present conditions. So, for example, silicon is a very important device in terms of the present electronics industry, and so if a qubit is built based on its property, then it has a very high chance of its applicability. So, these are the issues which also come into play when these are being looked at. So, here for example, the spin Hamiltonian can be looked into in mathematical sense now. So, there is this applied field which is interacting for these conditions. So, as a result of the external field, the spin of the system can have different parts which are shown here. Effect of the total Hamiltonian spin is a result of these different parts: external field, electron nuclei interactions, nuclear interactions, and they are composed of different parts. The effect of external field is due to Zeeman effect because of the applied magnetic field. It can give rise to that. The nuclear spin could also have a Zeeman term due to the. So, there would be two parts. One is due to the electron spin, the other one would be the nuclear spin, and then the hyperfine electron nuclear spin interaction is the other part, which is due to the electron nuclear interaction, and then finally, it is the dipole nuclear spin interaction, which is due to the nuclear part by themselves. So, there are all these different parts which give rise to these different interaction Hamiltonians, which are forming the part of the total spin Hamiltonian which have been looked at. The hyperfine interaction essentially is a result of two different interactions. One is due to the contact interaction, another one is due to the dipole interaction, giving rise to a final composite hyperfine interactions, which is given by a matrix as shown here, and they will essentially give rise to the spin conditions of the electron being changed. There are certain approximations which are being utilized in this particular final statement, which is being written in terms of the hyperfine interaction. It is only the contact only interaction is being considered under high magnetic field. The contact interacting high magnetic field interaction is only along the direction of the applied high magnetic field, and so this makes this interaction much more easy to be handled as compared to a general term. So, the energy level structure under the high magnetic field therefore results in this kind of a splitting into different terms, where the interaction finally is left to the hyperfine part, which is going to be doing most of the job here, and so the donor electron part in this case is going to interact. However, if the nuclear under the low spin condition, it's another approach. So, the donor electron spin in case of the high magnetic field makes it possible for the different states to be easily coupled, and there are so many different options which become available as a result of this interaction, and it's in some ways easier because it's only the Z interaction which is to be considered because of the highly strong field which is being applied. However, under the low field condition, it's not that easy. because there is a lot of coupling which still remains, and the separations are not very large, and the couplings cannot be just due to only one of the interactions. There are many other interactions which become possible. As a result, there are the interactions can be looked at as a result of the integrated effect of all these different conditions, which have been addressed also in recent work by another group, where they have shown how the magnetic field is interacting in terms of the low field conditions, and that there is a decay time associated with this process, and within that decay time, however, there are it is possible to still do the interaction and study them. In case of the high field case, it is possible to apply specific pulses to look at the interaction of one kind or the other. The electron spin system can be separately looked at with respect to the nuclear spin system, and their overall interactions can then be studied interestingly. So, for example, the electron in case of the high field system would be going from, say, the ground state to the excited state, whereas in the nuclear spin system the rotation would be changing with respect to the applied field system. So, the hyperfine modulations of an electron spin qubit would be possible to be seen when this has happened. The threshold value for the magnetic field for a fault tolerant phosphorus 31 electron spin qubit has been determined to be quite low at a threshold of 9 Tesla. So, this is some of the work which have basically been applied to show how these can be the modulations of the electron spin qubit can be looked at very carefully, and it can be essentially made to be fault tolerant under the conditions of the experiment. So, aspects which are similar to NMR has also been attempted here, because it is essentially the nuclear spin, and so a spin echo condition of where the nuclear spin is being recovered has also been showing that the coherence of the system is very easy to be kept and modulated, and it can be transferred as a result of these interactions. So, it is a very useful approach, and the high field limit, it is easier to understand and work ahead with it. So, the conclusions of this part of the effect in terms of the donor electron interaction for nuclear spin has been that the effect of nuclear spin bath on the decoherence of an electron spin qubit in a silicon phosphorus system have been studied heavily by many groups. New measure of decoherence process have been developed over the years by several groups in this process, and at low field region the coherence of the qubit exponentially decreases with certain characteristic time, which is roughly the claim of about a 0.1 microsecond. At high magnetic field region, the quantum operations with qubit produce deviations of a quantum state from ideal one. The characteristic time for these processes are about 0.1 microseconds. The threshold value of an external magnetic field required for a fault tolerant quantum computer for using an electron spin qubit in a silicon phosphorus doped system is of the order of an external magnetic field of 9 Tesla. So, it is a large magnetic field which is necessary, but under those conditions it is possible to use it as a very effective system for quantum computing implementation. So, we have tried to look at several other peripheral aspects of implementation of quantum computing, which are close enough to the ideas that we discussed earlier, but there are many variants, as we have actually shown in many of these areas that we looked at in this particular lecture. And so, in this week we have focused on trying to see how the very different approaches of quantum computing implementations are sort of connected to the basic idea of our development that we were doing in terms of understanding the quantum computer. And although it is quite difficult to still have a very easy implementation over the overall quantum computer, it is at a step where certain implementations are growing to a level that at least one system, as we discussed earlier, is commercially available, and there are many more which are waiting to get to that phase. So, hope exists, and we will see how these are now translating to further advances in the next few lectures that are left with us in the upcoming weeks. Thank you.